All right, Calculus 12, how's it going today? Hope you're having a good one. Here we go. We're going to be looking at antiderivatives. This is good times. This is the reverse of derivatives. Now, why would anyone ever want to do antiderivatives? Well, it's no different than why would anyone ever want to subtract, because subtraction is just the opposite of adding. Why would anyone ever want to divide? Dividing is the opposite of multiplication. There's obviously applications of it, but in math, sometimes we just do things backwards because we like to undo things in math and make sure the process can go both directions. So antiderivatives in the textbook are in these three places, or they're all over, but right now we're just going to end off with kind of just a random spattering of kind of what you would end up doing in a second semester university calculus course. So here's the game. What I want you to consider is, if I had given you, first of all, a function, call it big F of x. This is not the antiderivative game yet. The derivative you would know by the power rule would be 2x. Also, if I gave you the function x squared plus 7, the derivative would then also be 2x. So the question now lies, kind of from an antiderivative point of view, if you knew the derivative was 2x, what was the original function? That's the question. And just using logic and these two little simple examples here, we kind of know that the derivative of x squared would give 2x, kind of going backwards. So the power here was 1. So going backwards, we know we had to make the power 2. But with the power rule, if we check it, the 2 comes down and takes care of that. But then if you notice here, any constant's derivative would then end up being 0. So because this could have been plus 7 plus 71 plus 719, those all would have had the same derivative, then we're going to write this with a plus c, a big C for no particular reason. Just means plus any constant. So that's a constant, plus c. So that's kind of the antiderivative game, going backwards. Obviously going this way, no troubles. Done that so many times since the beginning of the course. Now we're going to go the other way, just using your wit. So here's the game. Here are a bunch of derivatives. What was the original function? So this is big F prime. So what is big F? So let's look at this, and just again, I would usually in class just let you play with this and just use your wit, and really just use your wit. Use the derivatives that you know, working forwards, and then work backwards with it and check it just by doing what you've done. So let's look at the first one. What function's derivative would be 3x squared? How I look at this personally is, I know if it was an x squared, where it would have come from the power rule before, would have been 1 higher. So it would have been x cubed for sure, because this would have to lower from a 3 to a 2 with the power rule as you went to take the derivative. But now the coefficient up front is a 3. Is that enough to take care of it? Well, yeah, it would be, because when you take the derivative of this, the 3 would come down through the rule and then lower to a 2, so that just checks out right away just by logic. So thank goodness that was a 3. If that was something else, we'll talk about how you would deal with that by logic. But then because you can always have a constant, all these antiderivatives will have a plus c. Let's look at the next one. 7x. What function did it come from such that 7x is the derivative? Well, this is a power of 1. We know that it must have come from an x squared with the power rule. It had to have come from there. But then if the 2 was there, the derivative of x squared would have been a 2x, not a 7x. But remember, I can put any constant here with the constant multiple rule that won't affect it. What number should I put there such that when I multiply by 2 gives back 7? I could put 3.5 or 7 divided by 2. And let's just check it. The 2 can come down, cancels out that 2, you get 7x to the power of 1, and then plus a constant. 3x to the 10th. What is the antiderivative of that? Well, the power must have been an 11. I know now that'll definitely turn to a 10 when I subtract 1, but the 11 would have been up front, but I want a 3. So what number times 11 would give 3? Well, how I deal with it, first of all, if I don't want the 11 to stay, I can put 1/11th and that'll cancel out the 11, but I can put a 3 up top, 3/11ths, because the 11 would cancel out the 11 on the bottom. You're left with a 3, and then there's your plus constant. 31. What's the antiderivative of 31? Well, it would have to have been 31x plus c. What about x to the n, where n is a constant? Well, using the same logic as this one here, we know the power has to go up by 1. So this would have to be x to the n plus 1. But you want the coefficient out front to be left with a 1. So how do I get this n plus 1 that's coming down away? Well, I could have the coefficient out front being a 1 over n plus 1 plus c. So that's kind of like, that's like the reverse power rule, if you want. Okay, sine. What function's derivative is sine? Well, knowing your trig rules, the derivative of cosine is linked to sine, but if I put cos here, the derivative of cos is negative sine. I want positive sine, so I need a negative out front, because the derivative of cos would be negative sine multiplied by the negative, which would give you positive, and then plus c, as we need a constant. So you just got to be careful. You just got to think. Remember, we're not taking the derivative of sine. We are finding a function whose derivative is sine. So it's got to be careful. What function's derivative is cos? What's the antiderivative of cos? Well, is it sine? Is the derivative of sine cos? Yep, there it is. Done. Plus c. Sine of 7x. Well, if the 7 wasn't there, we would definitely know it would be negative cos, because the derivative of cos would be negative sine times the negative would be that. But we need to have the same argument of a 7x there in order for the 7x to be maintained. But now with the chain rule, the derivative of this would have had an extra 7 coming out in front. So I need to put a 1/7 out front in order for that to cancel, for lack of a better word. And then I would just check it. Is the derivative of this this? Well, the derivative would be, derivative of cos is negative sine times negative 1/7 would be positive 1/7 sine 7x times the baby, which would be 7. 7 times 1/7 is 1. There's the winner. So you just check it. What's the antiderivative of secant squared? What function's derivative is secant squared? Well, using your knowledge of derivatives, you know that the derivative of tan is secant squared. So the antiderivative of secant squared is tan. E to the x. Well, the derivative of e to the x is e to the x. The antiderivative of e to the x is e to the x. What about e to the x, e to the 3x? Well, you know it has to have an e to the 3x in order for that to maintain. But then the inside derivative would be a 3, so we need a 1/3 there with the chain rule in order to counteract that. Hopefully everything will get some sunshine coming in here. Maybe I'll open up the blinds here. I don't know how to do that. Sorry, it's going to be it's kind of weirdly shaded there. One sec. There. I don't like taking the sun away, but I'm going to have to for the moment. It's weird day. Okay, cos of kx. Well, again, if it was just cos, it would be sine, but it has to be sine kx. The power, or the chain rule of this, I need a 1 over k out front, because k is a coefficient, or k is a constant. It can cancel out with your chain rule. Alright, so literally you just have to just use your wit backwards with these, and check the answer by taking the derivative of your antiderivative to see if it goes back to the original. So, another guy, just phrased differently. If dy dx is e to the negative x, find y. That's basically another way of asking the derivative. They've given you, sorry, the antiderivative. They've given you the derivative, you're going backwards. So again, just use logic and say, well, I know in order for e to the negative x, it must have an e to the negative x. But the derivative of that would have had a negative 1 come out, so you need a negative out front to counteract that. And plus c. And just double check your work. Take the derivative of that. Yep, it will give you this back. Next one gives you the derivative function, find y, so there's an antiderivative, we're going backwards, and you know that y passes through the point 1, 9. Okay, so let's start with y first. So here we're going to take the antiderivative. What function gives you 3x squared? Well, that has to be x cubed. That takes care of the power with the reverse power rule, and it takes care of the coefficient coming down. To get a 4x, you know it has to have an x squared. The 2 would have come down, but I need a 4, so I need a 2 there to multiply together to give the 4. And to get an x, or to get a 1, you need an x, and don't forget the constant. Now, this is called your general antiderivative. But now, because they're wanting us to find it at a specific point, you're now going to find the specific antiderivative. So we know if it passes through the point 1, 9, when x is 1, y cranks out 9. So then I can go and find c. So watch this. I'll make the y 9. I'll make the x 1. And I can solve for c. So 9 equals, so this is 1 plus 2 plus 1 plus c. That adds up to 4. So solving for c must equal 5. Therefore, our specific antiderivative must be this function. The derivative of it goes back to this. It's like a game. Yep. And when I plug 1 into the x's, it does crank out a 9. So there's your specific antiderivative. So sometimes they call this antiderivatives with initial conditions. Because they've given you some initial conditions to satisfy. Kind of fun, it's just like a game. Think of this as a game, no different. Now, interesting notation for this. So here's the notation that has come over time to denote antiderivative. If someone writes, it looks like a long elongated S. Almost looks like if you had a violin, like some of the violins, the front of the violin has that shape carved out of it where the sound comes out of. Just coincidence that it's like that, but it kind of has that look to it. This is called the integral symbol. Integral symbol. This part of it is the function that you're integrating or taking the antiderivative of, and that's called the integrand. And then this little dx is kind of a little bit of a flavor or a note of derivatives in there. That's just with respect to variable x. Now we'll talk about more of that in the next lesson of kind of where this notation has kind of come from. So this is basically saying what is the antiderivative of 4x, and it's called an indefinite integral. So you could look at that, and if you rephrase this as this, well then you could just literally say, well, I know, and you would just say the integral of 4x dx is equal to, what's the antiderivative? It must be an x squared with a 2 plus c. So that's just a really shortcut way, if you want, of saying what's the antiderivative of 4x. There it is. There's the general antiderivative, or an indefinite integral. Now, we haven't talked about why they use the word integral. We haven't talked about where this notation came from, but it just exists. So we'll talk about that as time goes on. So now they would give you a whole bunch of questions in regards to that notation. So here when you see this, the integral of e to the negative 3x dx, that is just asking what is the antiderivative of that function. And just like you did that little game before, you'll go, okay, well, I know it has to have an e to the negative 3x, but I'll need a negative 1/3 out front to counteract the reverse chain rule, so to speak, and then a plus c. There's my answer. Done. That's all it is. Like, once you know what it asks, it in some ways can be simple. Now, are they always going to be very witty and simple to do? In the beginning, yes, but as time goes on, as you take the whole course in the second semester, you'll get into ones that you just cannot do by wit, and you'll learn other processes to deal with that. At the moment for our course, it's just going to be using your wit. So here they put brackets around this whole thing because they want us to do the antiderivative of this. So, got to be careful. X to the negative 7. Well, using the reverse power rule, I know that this must go up a power, and up from a negative 7 is negative 6. Because if I think about it, that negative 6 would come down. This would lower by 1 to a negative 7. But I don't want a negative 6 out front. I want an imaginary 1. So I'm going to have to multiply by a negative 1/6 to give me back the 1. And there's the winner for that. For sine, I know sine, the derivative of what function gives sine, must be a negative cos, as we talked about before. And I'll need a 1/3 out front, plus c, to cancel out. The 3 would cancel out with the chain rule. And I would just double check that. Okay, derivative of cos, negative sine, multiplies this, positive, the 3, chain rule, boom, good. Next one's almost so easy it's hard. Integral of, like, there's white space here, dx. There's an imaginary 1 there. So that's just basically saying what's the antiderivative of 1 with respect to x? Must be x. Now if that was dy, this would just be y plus c. If it was dm, it would be m plus c. It just tells you what variable you're dealing with. Next guy, antiderivative of the square root of x. Well, before I do anything to that, I'm going to rewrite this as a power. And notice I didn't do any work, so I kept the notation the same. I'm still doing the integral of x to the 1/2. Well, reverse power rule, I know this must go up by 1. So 1/2 plus 1 is 3/2. And then when that comes down, I want it to be counteracted to give me a 1 back. So I'm going to put a reciprocal of it out front. So that comes down, cancels out to give 1, lowers by 1 to 1/2, and then plus c. Done. Last little guy on this page, integral of 1/x plus 1/x squared. Now this one's kind of a weird one. First of all, you could look at this and go, well, let's write it with powers, just because we can think better that way. And this one's kind of a little bit of a tricky one. I only know it's tricky because I recognize it. If you start playing with this one for a minute, if the power goes up by 1, you might look at that and go, oh, it has to be a power of 0. But as soon as I make x to the power of 0, that's now a constant of 1, and the derivative of 1 would not go back to 1/x. So this is kind of a little bit of a, like, what's going on? The reverse power rule for -1 does not work. But you should recognize, this is kind of a sneaky one, what function's derivative is 1/x? That's sneaky. That's ln of x. Remember the derivative of ln is 1. So that's a sneaky one. That's one that can't be done with reverse power rule. That's just through knowledge. Technically, it's the absolute value because here x could be positive or negative, just can't be 0. So remember we talked about that in the one lesson. It could be ln of absolute value of x. But if you didn't put the absolute value, not the end of the world. And the next one here now, -2, that can be done with, because remember this is going to go up by 1, that'll be a -1, and then I'm going to have to put a negative out front, such that when I take the derivative of this, the -1 comes down, multiplies that negative to make it positive, and then that'll lower by 1 plus c. So that's kind of a sneaky little dog. So anytime you have a -1 power, it's going to be a ln related to it. Anything higher than negative or lower than -1 if you want, we can use the power rule. Last two, and then we're done. Okay. So here goes this guy. Looks like an absolute rat's nest. Don't forget I need the dx there. So we're taking the antiderivative of this. And because this is a horrible rational, the only way out of this is to write this as separate individual fractions. I'll make that into a power. And then clean this up. So I still haven't done any antiderivatives yet. I'm just cleaning it up. So this will be 3, and then x over x cubed would be x squared on the bottom, so it'll be -2 power. Here that would cancel out to give me 9 over x, or x to the -1. Here, this guy is ugly. If I put this, so this would be that, and it would be 1/3 minus 3. So 1/3 minus 3, this would be 9/3, so it would be negative 8/3. So now I can take the antiderivative. So for this guy, I know it has to go up by a power, so that'd be -1, because I'm doing antiderivative. This would then have to be a -3, such that when it comes down, I get positive back, that lowers by 1, that works. This one, don't forget, this one is 9 times 1 over x. The 1 over x one is the sneaky one, that's ln. That's the one you gotta be careful with. And the next one here, -8/3, I need to raise that up by 1. So if I add 1 to this, -8/3 plus 1, that's 3 over 3. That will end up giving me -5/3. And I want a +7 left over, so I know it has to be a negative. I want the 3/5 here to cancel out with the 5/3, and I want a 7 to stay behind. So let's just rewrite all of this. So I end up with -21/5 x to the -5/3 plus c. And I would just double check this, does this work? So the negative comes down, multiplies that, the 5's cancel, and you get 21 over 3, which is the 7 back. This gives me 1 over x times the 9. Yeah, all works out. So just a fun, weird game. You know, I have the morning Sudokus and crossword puzzles. They should have the morning antiderivative in the newspaper. I'd buy more. Okay, next one. Now this one's kind of a little bit of an odd duck. There are different ways of doing this as you learn more techniques, but at the moment, the only way that you could do this with sheer wit would be to look at this and go, I kind of recognize that a bit. On your trig identity sheet, double cos is 1 minus 2 sine squared x. So it's basically this with the negative sign. So negative cos 2x is -1 plus 2 sine squared x. So you could replace this with a trig identity as negative cos 2x. And now you could take the antiderivative of this. So the antiderivative of cos, negative cos, would be negative sine with a 2x, but I need a half out front to counteract the chain rule, plus half. And let's double check. Derivative of sine is cos with a negative, good. Inside stays the same, 2 comes down, done, and then that would work, which then you can go back to there. Now you can try doing this another way, but that's the best way to do it. Sometimes you got to be sneaky and lucky at the same time. Okay, so that is antiderivatives. Over and out.